Hi, my name is Norluqman Hakim bin Azaume and my ID is 25242. So today my group will present about our topic, which is the application of inverted Lambda-Mu-Rho LMR for determination of hydrocarbon zone. Continue with the table of content. So we'll start this presentation with the introduction of AVO, and then we'll move to the introduction of AVO inversion, and then we'll explain about the LMR inversion, and continue with that we will proceed to the pros and cons or advantage or disadvantage about the LMR inversion, and then we will proceed with the methodology of the AVO inversion, in which we will use this technique of LMR inversion, and lastly will be the result for this technique. I will talk about the introduction of amplitude variation with offset (AVO). So variation of seismic reflection amplitudes with offset (AVO), or alternatively reflection angle of incident (AVA), are applied to pre-stack reflection observations, where it develops a way to use this information to predict contrast in rock properties at depth on a reflecting interference. Theoretically, amplitude variation with offset (AVO) has the ability to discriminate between true gas-saturated bright spots, and manifolds brine-saturated bright spots. So next, AVO analysis thus enables us to extract the additional elastic properties from different range of offset within the pre-stack seismic data. The typical gas sand has a lower acoustic impedance than the saline shales and will produce a negative reflection coefficient at near offsets. The magnitude of these reflections get increasingly larger or more negative with offset if class 3 AVO response. So next is a brine field lithologies will have a reflection coefficient which the magnitudes of this reflection will decrease or dim out as the offset increases. So bright spot analysis on stacked data is very convenient because stacked seismic data are generally more readable available than pre-stacked gathers, and stacked data generally have a much higher signal to noise ratio (SNR) than the pre-stacked data. Continue with the introduction. Without consideration the amplitude response with offsets, however, the ambiguity of uncertainty of geologic interpretation behind the bright spot is greatly increased. So this figure shows an example of bright spots, which is a post-stack amplitude anomalies, which in this basin caused by different types of geological condition. So based on this figure, it shows three bright spots, and only commercial gas reservoir is showing at the shallowest reflector, and the well was extended to the target of two deeper bright spots, which turned out to be a non-commercial tight silk with gas, and below that is a brine saturated silk. And next, I will explain a bit about the amplitude variation with offset AVO inversion. So, this AVO inversion techniques or that will be used is the Lambda-Mu-Rho inversion, which is very effective to discriminate between gas-saturated and brine-saturated post-stack bright spot. Using this method, it can reduce the uncertainty and clarify the risks associated with the drilling bright amplitudes. Through the AVO inversion, the data volumes can be created, which specific of rock properties represented by the seismic attributes, which incorporated amplitude, with offset behavior derived from the pre-stacked seismic data. These volumes may be displayed in a manner similar to conventional display of stacked seismic data amplitudes and can be interpreted in somewhat similar fashion. The AVO-derived seismic data are calibrated to log measurement and then explorated away from the borehole throughout the volume. Moreover, instead of an interface property such as reflection coefficient, meaningful numerical quantities associated with the reservoir may be obtained from the extracted data volume. Thus, these derived AVO attributes are portable and both absolute and relatively comparisons of AVO attributes are facilitated.
Hi, I'm Aliff Rusli. I will talk about the Lambda-Mu-Rho inversion. So this is one of the technique of AVO inversion. It is done by pre-stacked seismic ampligators are inverted to extract data volumes of LAM's elastic rock parameters, which is lambda and mu, combined with density to form lambda-rho and mu-rho. So why did we choose lambda-rho? Lambda is a sensitive fluid indicator. In compressional velocity, it uses the parameter lambda to show low values for gas-saturated sand. So, because gas is compressible, lambda rho will always show low values and indicate gas saturation. Another parameter is mu-rho. Mu is insensitive to fluid saturant, so we can use mu-rho to indicate matrix. And for the reservoir, sand should show a high value in mu-rho because it is dominated by quartz, which have higher rigidity than clay minerals. So when we are looking for a hydrocarbon zone, we are going to find the zone with low lambda rho value and a high mu-rho value. The good thing about using lambda-mu-rho inversion is it uses elastic constants directly, so we can get a more meaningful result than using post-stack amplitudes alone. The disadvantage of using this method is it is computationally expensive to reduce reflection coefficient on amplitude preserved pre-stacked ampligators. So this could lead to amplification of noise. And number two, it is the sensitivity to noise could corrupt the results, making interpretation of data absolutely useless.
Greetings, my name is Othon Biquiza, and I'll be talking about the methodology. As you can see on the workflow, we first begin with loading the data, well data and seismic data, and then we apply quality control to it in order to remove any spikes and identify the anomalies present in the seismic data. And then we proceed with the well-logged data analysis to define the potential hydrocarbon accumulation zone. And then we move to the gas-man fluid substitution to model different fluid scenarios. And then we do the feasibility study to determine the effectiveness of the Lambda-Rho and Mu-Rho elastic parameters in distinguishing lithologies and fluid distribution. And after that, we apply seismic to well tie in order to match the seismic data to the well data in the time domain. We then proceed to the seismic data, where we first interpret the horizon. We define the zone we were about to interpret, and after that, before we apply the seismic inversion, we need to generate the low frequency model. And then after that, we apply the pre-stacked simultaneous inversion. We extract the elastic properties, and afterwards we generate the lambda-mu and the lambda-rho and mu-rho for further interpretation. Before we generate the lambda-mu-rho, we first conduct a feasibility study to the well log data. So the first step is to apply the fluid substitution model for different fluid phase composition and generate new elastic and density logs. We then, using the elastic properties obtained from the well log data, we build the cross plot of Lambda-Mu-Rho for lithology and fluid discrimination. And we expect to have a low Lambda-Rho and high Mu-Rho for sandstone, as seen on the picture, on the figure. We then proceed to prepare the seismic data to apply the pre-stack simultaneous inversion. The first step is wavelet extraction. We expect the pre-stack seismic data to experience continuous loss of high frequency energy from near to far offset, and each CDP gather will be identified by different wavelets. We then use the sonic and density log to generate the synthetic seismogram. We then use depth to convert the depth to time by using check shot data to tie the well data to the seismic data. We then interpret the defined zone, the defined potential hydrocarbon accumulation zone, and we expect to find low gamma ray, high resistivity, and low water saturation. We then proceed to generate the low frequency model. We need to generate the low frequency model because we need to obtain absolute impedance values. Without the low frequency model, we cannot obtain absolute values. We instead obtain relative values. And that can be done by extracting it from the well data and adding it to the seismic data. We then apply the simultaneous inversion, in which we use the IK-Riches equation to generate a synthetic trace using convolution. And then we extract the P impedance, S impedance, and density. And we then conduct a quality check by cross-plotting and comparing the results with well data. The last step is to generate the Lambda-Rho, Mu-Rho, and we do this by transforming the inverted elastic properties into Lambda-Rho and Mu-Rho, and then we build the cross plot of Lambda-Rho and Mu-Rho to identify and interpret the potential hydrocarbon zones.
Okay, next moving on to the next part, which is the results part. Diff both figures showing the Lambda-Rho and Mu-Rho volumes that is generated from the LMR inversion, which is Lambda-Mu-Rho for the Columbus Basin. This inversion is also limited to a specific time window, which is centered on the three target horizons, which is horizons A, horizons B, and horizon C. So these solid colors here outside the zone are considered null values. Among the CMP stack high amplitude reflections shown in the figure 1, which is at the part of the introduction, only the shallowest horizon A is showing a truly lithology, which is the lithology gas saturated sand. And also we can see here at this left hand side figure, this figure have the lowest value of Lambda-Rho here, which is indicates by the bright green, and for the right hand side figure showing that only the horizon A has the highest and most spatially extensive Mu-Rho values, which is indicates by purple color. That is correctly indicating the sandy lithology. However, for these both horizons, horizons B and horizon C, also shows a low lambda-rho values that is relative to their surrounding lithologies, but it is clear that these values are not comparable to the gas sent at horizon A. Next, moving on to the other parts of the results, which is we can see on the left hand side is showing the limited numerical ranges of lambda-rho and Mu-Rho values on the color display, so that we can see the truly anomalous of low lambda-rho and high Mu-Rho zones that are highlighted. Even though there are some Mu-Rho values around horizons B and C, but it's not considered as a sand body because there is no special consistency to suggest the presence of a continuous sand body, as is the case at the horizon A. Okay, as we can see here on the right hand side of the slide, this figure is showing the lambda-rho and Mu-Rho map views of the distribution that is extracted along the horizon A. This dotted polygon indicates the general location of the field. Again, the coincidence of the low lambda-rho and high Mu-Rho along horizon A indicates that this is a gas saturated sand that has been successfully identified. Okay, next moving on to the last part of this result. The left hand side shows the typical Lambda-Mu-Rho crossplot, which the function is to facilitate more effective and convenient interpretation of lambda-rho and Mu-Rho because we can see the coincidence between the two rock properties. The data points is used on the crossplots are from the same lambda-rho and Mu-Rho from the figure at the earlier part of these results, and the superimposed colored zones highlight and classify the values in the same manner on the seismic data as shown in the right hand side figure. The result, as we can see here, the result is visually clearer for the interpretation of the predicted gas saturation. The horizon A is colored red because it identified as a gas sand, so that it alone appears as truly anomalous compared to the other surrounding lithologies. The location of the gas-water contact also is observed in the LMR cross-section on the right-hand side figure, as the reflector changes from red to blue down deep.